is Christine Atuhaire, and I'm going to be sharing the work that is still in progress but almost completing. It's looking at exploring the use of satellite imagery in monitoring air pollution, and specifically, we are looking at the pollutant called PM 2.5. So, air pollution has become a major threat in almost all cities and urban areas around the globe, and Kampala city or Kampala district has not been spared either. So particularly the research is looking at PM 2.5, which is a pollutant, and this means particulate matter with diameter less than 2.5 micrometers. So various research studies have identified it as one of the leading pollutants because these particles are very small. It is highly inhalable, so it has been linked to various respiratory diseases, and this has raised the attention of various researchers and the public to monitor the concentrations in the atmosphere. So one of the strategies that has been put up to monitor these concentrations is through establishment of monitoring stations, and specifically in Kampala, this is being done by Kampala Capital Authority, CCA, and then AirCo, which is a university-based setup here in Imagery. So KCCA has around 25 monitoring stations in Kampala, while AirCo has around 25 stations. So this is a good initiative, but however, it has come up with still some challenges that need to be addressed. One of them being that what we can get from these stations are just point measurements, meaning that the measurements relate only areas where those stations are. And then secondly, when you look at the spatial distribution of these stations, most of them are located within the urban area, meaning that areas outside the city center, we cannot easily detect or know how much concentrations of PM 2.5 are there. So this takes me what the research was looking on, or what it tends to address. So we are saying, much as we are getting accurate measurements from the ground stations, these stations are prone to vandalism. It can be by people or even extreme weather conditions. So what that brings about is data gaps. So that means we cannot adequately or continuously have measurements about PM 2.5 concentrations in Kampala. So therefore, this research looked at how we can explore the use of remote sensing data to monitor particulate matter concentrations in Kampala, and as a way of supplementing the deficient ground monitoring stations that are available. So the main objective was to determine satellite-derived PM 2.5, and then the specific ones, first one is to characterize variations in aerosol optical depth. Aerosol optical depth, those are the satellite aerosol measurements. And then secondly, correlate the satellite observations and ground observations to determine satellite-derived PM 2.5. So the methodology that was used, mainly we are looking at Landsat and Sentinel-2 images, so that there are two sensors that were employed in this research. And then we are looking at meteorological data, because satellite observations are taken under the influence of weather conditions, so there is need to incorporate that. And then finally, the in situ measurements, which are PM 2.5 measurements from the ground monitoring stations. So the first thing was to compute aerosol optical depth, which is the AOD, and this was done using the Christine algorithm. So from the AOD, our first objective was to characterize or understand these variations. However, we cannot understand these variations without putting into consideration of the meteorological data. So that's why our characterization of AOD was based on meteorological data. So we did the spatial characterization, which is identification of hotspot areas, the high and low concentrations. And then the second bit was on temporal characterization, and this we looked at how aerosol concentrations are varying in the different seasons. And then also we looked at how does the AOD measurement relate to meteorological data. So from that, we moved to the objective 2, which is determining satellite-derived PM2.5. And in here, we are using a relationship between AOD and ground PM2.5 to estimate the satellite-derived measurements. So to do that, we came up with 2 models. One of them was looking at the seasonal model, modeling the relationship seasonally, and in another model, looking at modeling this relationship as at each satellite overpass time, which we called the time-specific model. So the two models were evaluated, and then the best that best describes the relationship was used to estimate PM2.5 from the satellite observations. So some of the results that we have. So like I said, the first thing was determining aerosol optical depth. To understand the aerosol optical depth, this has been grouped into the different seasons. So we have Sentinel and Landsat. Landsat, we have only one image because the images that could be available at that time, the ground observations were missing, so we could not use them into the analysis. And then the other thing was about cloud cover. So that's what reduced the satellite, the Landsat images. That's why we ended up with one. And also given that Sentinel temporal resolution is 5 days, it is easier to have many more images of Sentinel than Landsat 8. So what we can get from the distribution of aerosol temporary, we can see that within the wet season, the AOD values are higher compared to the wet season, because we can see within the dry season, the measurements are ranging around 0.4 to even greater than 0.7, which is high concentration. Whereas in the wet season, we are looking at most of the observations being between 0 and 0.4. So that one tells us already the seasonality within the AOD or the satellite observations. So to further do the characterization, now we look at how these observations relate to meteorological data. And for meteorological data, we are looking at wind speed, air pressure, temperature, and relative humidity. So the first thing that was done was to look at the linear relationship and also look at the non-linear relationship, how they relate to each other. What is clear in both in the wet and the dry season is that the linear relationship between AOD and meteorological data is very weak. So that means that the variations within satellite observations are complex and cannot be modeled using simple linear regression equations. Whereas when you look at the nonlinear relationships, the relationship is strong, and this tells us the contribution that meteorological data has on the AOD variations. So when we look at the spatial component, the spatial variations, we want to see how these variations are changing from one place to another. And in here we did the hotspot analysis. So what we can observe from here is that also the hotspot areas are not constant. They are varying from one place to another as at each satellite overpass time. But what is clear or what is consistent is that most of these hotspot areas are occurring along transport routes and within the CBD. So that means that the activities along those areas contribute to the high aerosol concentrations. And this can further be explained from this slide. So an extract of one of the hotspot areas, those who are familiar with Kampala, this is around Kampala Mukono Highway near Spear Motors. So when you look at that area, there are a lot of activities that take place there. One of them being that we have a road junction, yes, the road that goes to Tuntinda. We have a containers depot. We have a factory, Pepsi company around the same area. And then we have a garage that is situated along the road. So all these areas, or all these locations contribute to the aerosol concentrations because there is a lot of emissions from the vehicles on the road, from the factory that is relocated there. So it explains why we have high aerosol concentrations within that area. So that is on the spatial variations of AOD. So moving further to estimate RPM 2.5 now, we said we are using two models, which is and then the time-specific model. So an evaluation was done on both models to determine which one best represents the relationship between satellite observations and ground observations. So from the evaluation, it can be seen that the time-specific model, which models the relationship between AOD and ground PM 2.5, is best explained when we look at it at each satellite over past time, not combining the entire season, let's say the wet season or the dry season, because we see when we look at each satellite over past time, the variables are able to explain the variations within PM 2.5 beta when we consider the time-specific model. So that is the model that was adopted to estimate PM 2.5 measurements. So as we can see from that, then of course we did the dividing of the data or subsetting into two parts, the testing and then the validation set. So using the validation set, we can see that the model performed moderately well because about more than 68% of the variations within PM 2.5 could be explained by meteorological data and then the satellite observations. So when we look further now from what we have estimated from satellite observations, we can see that as at that time when the satellite passed over Kampala, within the dry season, Kampala was experiencing unhealthy concentrations for sensitive groups and some bits of unhealthy for all. So meaning that the pollutant concentrations at that time were very high and very unhealthy. Whereas when we look at the wet season. When we look at the wet season, the concentrations were moderate and even good at some point. So this already takes us back to what we saw at satellite observations, explaining the seasonality within the observations. And it can be seen that even the ground observations that we have estimated from satellite observation also show us the seasonality within the concentrations. So to perform the validation of what we came about, we used the validation set, and this was not used within the testing data. And we used correlation between the estimated and the ground observations. So from the coefficients, we see that the R-squared values are ranging between 0.4 to even 0.9, which is moderate, meaning that the observations that were estimated or the satellite derived are representative of the ground measurements. However, as we can see that within the testing set, the observations that were used are different and they're actually low. And this was brought about by the issues that I already talked about, the missing data from the ground stations and the cloud cover within the sum of the images. So it is hard for us to rely on an R-squared of, let's say, 0.9 that is from 4 observations. So that's why we went further to use the root mean square value as an assessment of the performance of the model. So from the root mean square value, we can see that all our root mean square error values are below the minimum observed value at the ground stations. So that still tells us that the estimated PM 2.5 is still representative of the ground observations. So to still talk about the validation, we can see from this diagram that is the satellite derived, the mean, and then the in situ, PM2.5, the mean. So we can see there is not much variation. However, when we look at the Landsat 8 data that we have seen, we can see some big difference of underestimations. Yes, that is possible. However, at this stage, since we used one Landsat 8 image, we cannot conclusively say that Sentinel-2 performed better than Landsat 8 because the sample that we have is not big enough for us to make that conclusion. But nevertheless, still the performance can be compared. So, in conclusion, what we can say is that aerosol optical depth, which are the satellite observations, they are seasonal dependent and varies spatially, like we saw on the hotspot analysis maps. The hotspot areas were not constant, so it still varies spatially. And likewise, the relationship between AOD and meteorological data is not linear or is not direct, so we cannot explain it using linear regression analysis. And then, secondly, we can say that no single model can best describe the relationship between AOD and PM2.5. Like we saw that the model as at each satellite over past time was able to describe this relationship better than using a model that may be for the dry season or for the wet season. So that means the relationship has to be modeled as at each satellite over past time. And then lastly, the correlation between the satellite-derived PM2.5 and ground-based measurements still tells us that remote sensing data is capable of supplementing the deficient ground monitoring stations. Some of the recommendations that came up from the work is that for us to be able to use satellite data to monitor pollutant concentrations, we need to carry out operationalization of the model. So that means we need to put it in practice and see how we can incorporate satellite observations, ground measurements, and meteorological factors and all the other weather conditions to monitor our pollutant concentrations. And then secondly, that is future work that we recommend to be done on the operationalization. And then second recommendation is that, like we saw on the validation, the satellite observations or the satellite-derived PM2.5 highly depends on the amount of ground observations that we have. So for us to achieve objective one and be sure that what we are getting is right representative, we need to further densify the model. Yes, the initiative is good, they have done much, but there is still need room for improvement to densify the available network within Kampala. Yeah. Thank you very much.
Thank you very much, Christine. One question out of simply curiosity. From the hotspot map, is it possible to locate where downtown is?
Yes, it is possible to locate it, but it's around this place here.
I would imagine.
Yes, it's around there.
Great.